Okay, let's start. Good morning. So this week we're going to finish our discussion on the singular value decomposition today, rather. And then we're going to talk a little bit about dynamical systems. Dynamical systems is it's closer to my field of expertise. So I'm excited about that. And this is also very interesting. Before I remind you what we were trying to do with the singular value decomposition, here are two exercises. They are for you. These you can verify using the tools that you have at your expense or at your hand by now. So the first part is that if you have an m by n matrix, arbitrary matrix, then you have these two symmetric matrices, right? So A doesn't need to be symmetric, A doesn't need to be square, but if you have A, you can look at A transpose A. Now that's going to be a square and symmetric matrix. And likewise, you can look at A transpose. That too is going to be a square matrix that is symmetric. The exercise is telling you that the rank of A is going to be the same. So if A has rank 5, this symmetric matrix is going to have rank 5 and so on. The second exercise is that if I take two matrices, A and B, such that both AB and BA are defined, then really any eigenvalue of AB is going to be an eigenvalue of BA and vice versa. And if you have lambda and non-zero eigenvalue, then their algebraic multiplicities are going to match as well. If 0 is an eigenvalue of both of them, it is not necessarily true that the algebraic multiplicities of 0 is going to match. But if your eigenvalue is non-zero, then the algebraic multiplicities are going to match. And of course, you can imagine how 1 and 2 are related, because above we have A transpose A and A transpose. And here too, I have two matrices that I sort of flip. Using these two, you can say that the eigenvalues of A transpose A is going to be the same as the eigenvalues of A transpose, with the same multiplicities insofar as lambda is not an eigenvalue. Now, these are going to be important in the singular value decomposition. Okay, so we start with an arbitrary m by n matrix. And we want to do something like the spectral theorem to this, okay? But it is not necessarily square. Even if it were square, it is not necessarily symmetric. So there is no way to apply the the spectral theorem to A immediately. Let's also say that the rank of A is R. Okay, it's an integer. It can be at least 0, and at most the minimum of m and n, right? Because row rank is the same thing as the column rank and so on. So what we want is this. We're trying to reach to this. An orthogonal U, and I'm going to use this block matrix notation. So I want to think of the columns of U as splits, okay? So orthogonal matrices are necessarily square, but I'm saying that the columns I want to separate. So M against R by M minus R. Okay. So I want a U. I want another orthogonal matrix, V. And this time I want to split this as well. This time I want to split the rows of V according to this rank. Orthogonal V in R against n minus R times n, I want a sigma tilde that's going to be an R by R invertible diagonal matrix whose diagonal entries are positive numbers. I'm going to denote this by sigma tilde. So let me write it like this. Oh. Okay. So sigma tilde is going to be an R by R diagonal matrix whose diagonal entries are positive numbers. Such that, okay, so I have my u, v, and sigma tilde. Let me write it here. Sigma 1 is not less than sigma 2, which is not less than whatever, which finally end up at sigma r. They could repeat. I don't care about them repeating, but they're in descending order, and they're all positive numbers. And for sigma, this block matrix, who's 0 everywhere except the top left corner, where I get to see sigma tilde. So now this is going to be a block matrix of dimensions r against m minus r times r against n minus r. We have, or one has, A equals U sigma V transpose. Okay? So I split these channels for these transformations in such a way that this multiplication makes sense. Okay, so let's check this out or verify this. Let me write this bigger. So A is m by n, which means that U has to have m rows and V transpose has to have n columns. But then here I said that U is, so the columns of U are split as R against M minus R. And you see the sigma 2 is split like this. So it matches. And likewise here, this splits as R against N minus R. So this is what we want. Okay? Let me also draw perhaps a picture, a schematic for this matrix multiplication. So you see, even though the channels are split here, sigma is an m by n matrix. So it's a matrix of the same form as A. U is an orthogonal transformation, and V is an orthogonal transformation also. Now, I'm thinking of U and V as passive transformations, and I'm thinking of A and sigma as pretty much the same active transformation. Okay, so let's draw this. So let's say that A is something like this. Or maybe I should emphasize this further. So let's do it like so. Okay, this is my A. So this length has to match with the dimensions of M, of U. So it's a square matrix like so. And then in the middle, I have this guy, which looks like this. And then here I have V transpose, and its dimensions are going to match with this. So it's going to be a small one. Okay. Now let's also do this channel splitting. So let's say that the rows of U are not split, but the columns are. So R is somewhere here, let's say. This is R. And here too, I need to split it in such a way that this length matches. And I need to split here as well, so that this is a square matrix now. Okay? This is R by R. And here again, I'm splitting. Oh, this time I'm splitting the rows, as you see. So it should be like this. Okay. So this is where these non-zero entries go. Okay, in this box. Everything else here is 0. Okay. Here I have a bunch of columns. So I'm thinking of U as split like this, and V is split like this. Okay, and A is itself. Okay, so this is how you should imagine this. So let me write this as well. A U sigma V transpose. Now, what did we do? We said that, so we started with, well, let me also draw this picture as well. The important picture. So, that, and then I have this, then this, and then this, and then this. Okay. Then I want to have something here, something here, something here, something here. Then I want to have this, 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 this. Okay. So here I put A. Here I put A transpose. So this is supposed to be the same as this, and this is supposed to be the same as this. And here again, this is A transpose. Okay. Now, and these are all perpendicular. By the way, don't worry too much about putting this down on your notes for now, because I think in week 15, when we start doing this review, we're going to do some in-class activity, and we're going to sort of make our own map for this. It gets fold in like, I figured this out because I was avoiding doing my taxes. So I found out a nice way of representing this. You can just like fold this thing. And like whenever you fold it somewhere else, it gives you sort of like one piece of the picture. So it's pretty fun. So don't worry too much about putting this down accurately. We're going to do that later. So what we did last time was this, okay? We want to understand this guy, but that is arbitrary. Or let me write more things. So this is the column space of A, and this is the column space of A transpose. then this is the null space of A. And again, this is the null space of A. And this too is the column space of A. Oh, transpose. This is the column space of A. And now this is the null space of A transpose. And this too is the null space of A transpose. Okay. So here you get to see one instance of the fundamental theorem of linear algebra, and here too, and so on. Okay, and here too. Now what we did was this. We looked at, instead of this map, this whole map. Okay. So now let me perhaps put more things down. A is m by n, which means that it is from Rn to Rm. So this is Rn, this is Rm, and this is Rn. And this is Rm also. So if I look at this guy, it's a map from Rn to Rn. It's a square matrix, and it is symmetric. Okay? Now I get to apply the spectral theorem to it to say that it has an orthonormal basis. That is an eigenbasis too. And we call that V, or V1, V2, and so on. Putting those basis vectors into this matrix gives me an orthogonal transformation. Now you see this red guy is the same as this, but it is sort of like reoriented if you want. I'm going to call this R to the R. So R-dimensional real space. This V transformation, it's passive. It takes this guy and puts it in the right orientation for the column space of A transpose. Okay? Now, the null space of A, so the nullity of A is going to be n minus r, which means that this vertical guy is an n minus r dimensional space. And again, this orthogonal transformation is taking this vertical and puts it in the right orientation. I have the same thing here. R to the r, R to the n minus r. And here, because I got this by applying the spectral theorem to A transpose or AA transpose, this guy is going to be a diagonal matrix. If I want, I can write it like so. So this is V, A transpose, V transpose, which means that this is this can be written like so. Okay, so this is what we were doing. And I also defined these U vectors. I'm going to write all of them down in a second. But for now, let's write down the diagram. Now look, I can do the same thing to this guy. A transpose A, or AA transpose, however you're reading it. So if I look at this transformation, it is a squared matrix of dimensions m by m, which means that it's a transformation from this to itself, applying, and it's symmetric, applying the spectral theorem to it. Again, I get yet another orthogonal guy. And this is going to be A transpose U, A transpose U, transpose. Diagonal. Now this is, even though we're applying this, the spectral theorem to this box right here and to this box right here, in a sense, this V and U are coupled, okay? And here's how. So what we did was the following. Relative to A transpose A. Now, step one. A transpose A is a symmetric n by n matrix. Applying the spectral theorem to it gives me an orthonormal basis for Rn that is also an eigenbasis. I want to arrange these eigenvectors for A transpose A in such a way that these last n minus r vectors correspond to the eigenspace associated to 0. In other words, the null space of A. These is a basis for null space of A, and the remainder are a basis for the column space of A transpose. And here, you see, based on this first exercise over there, the ranks match, and so the nullities match as well. So this is really, you can think of it as the eigenspace of A transpose A for the eigenvalue 0. Okay? This is the eigenbasis decomposition. So let me write it like this. So the eigenvalues are going to be like this. A transpose A times Vi is going to be lambda I Vi. For some lambda I, they're going to be real numbers because of the spectral theorem. And further, since this is the eigenspace of A transpose A relative to 0, the other eigenvalues are going to be non-zero. Okay? So, yes, and further they are, okay, so let me write it like this. Positive okay, so we have this. And in fact, let me do it like this. Let me reorder. I'm imagining I'm taking these eigenbases in such a way that the eigenvalues are decreasing. And they're all positive numbers or non-negative numbers here. So let me write it like this. Okay. So A transpose A, I'm saying, has exactly R positive or non-zero eigenvalues, and the remainder, maybe they repeat. Okay. The remainder, though, are going to be 0, and the algebraic multiplicity is going to be n minus r. Okay. So that is what we wrote. Now, why are these positive numbers? Well, that's because A transpose A is a symmetric matrix. It's a square matrix, it's a symmetric matrix, but further it is positive semi-definite. Okay? Because it's coming from a norm, or it's coming from a quadratic form that is positive definite. So this is this. Then we said that if we were to apply A now to these basis vectors, all vectors after VR are going to vanish because they're in the null space. But the remainder are going to be still orthogonal. Okay, so that's the beauty. That's the benefit of looking at this. So that's step 1. Step 2, if I and j are not more than r and they're distinct, then a times vi is going to be perpendicular to a times vj. So I had these vi vectors in this space. I apply a to them, and I get now vectors in Rm. And I'm telling you that the first R vectors here, they're going to survive, and indeed they're going to land onto this red column space of A, and they're going to be orthogonal there. So orthogonal basis for the column space of A. Their norms could be different than 1, so you need to normalize them to get an orthonormal basis. Those normalization factors are the singular values. We computed that the norm of A vi squared really is lambda I. Okay? So this was something that I missed last time. I said I didn't clarify this very well. You see, you can see it here too. Because this lambda I is precisely the norm squared of AVI. Norm squared numbers are always non-negative numbers. So I know that this is non-negative. Okay? And I can take the square of it. Right, a square root of it to get sigma I. Really, when I'm taking the square root here, I'm not necessarily choosing. I mean, you can think of it as choosing plus or minus, but really, the sigma I I'm defining as the norm of A times Vi. And norms are positive numbers here. Okay? So, and that's the ith singular value of A. Okay, I can erase that. So that means that if I were to define U1 equals a V1 normalized, which is the same thing as a V1 divided by sigma 1, and then UR, same thing with A times VR, then U1 to UR is now going to be an orthonormal basis for the column space of A. Okay? Now, let's complete this to a basis for our M. Just to recap, we had V1 to VR here along this red space, and VR plus 1 to Vn along this yellow space. We applied A to them. The guys that were along the green one, they vanished because they're in the null space of A. The remainder are going to be in this guy, okay? And I'm saying that they're orthogonal, and then we normalize them to get u1 to ur here. But certainly I can complete this to a basis, which is going to be an eigenbasis for this symmetric matrix, okay? So by the exercise, so these are also the eigen values of AA transpose. These are also the eigen values for AA transpose. Now, this piece is going to match when I look at this matrix as well. And there's going to be a bunch of zero eigenvalues, but maybe the multiplicity is going to be different. Okay, the multiplicity of 0 for this different matrix is going to be not n minus r, it's going to be an m minus r. That's the only difference. The positive eigenvalues are going to be the same, with the same multiplicities. And in any event, just like this guy is the same thing as the eigenspace of A transpose associated to 0, this guy is the eigenspace of A transpose A associated to 0. So I can just as well complete this basis to an orthonormal eigenbasis for the other matrix. For Rm relative to, okay, I forgot which guy it was. Okay, that one. So now we have this. Let's also color code these. So I need the yellow and the red. The first R vectors here are going to be for the column space of A, and these are going to be for the null space of A transpose. Okay. So now finally, let me erase this. Reading these equations, we have this. Sigma 1 times u1 equals, or maybe I should write it the other way around. A times v1 equals sigma 1 times u1. A times v2 equals sigma 2 times u2. All the way up to A times vr equals sigma r times ur. These are what we had. And then the remainder are going to be 0, of course, if I were to do A times VR plus 1, because VR plus 1 is in the null space of A. But in any event, putting these in a matrix, you have this. So define V1 to be let me do it like this. R plus 1 Vn. So now V is an n by n orthonormal basis, orthogonal matrix, because these constitute an orthonormal basis. And I have U, and it's going to be like so. So V is going to be n by n. U is going to be m by m. This too is an orthogonal matrix. And you see there's this splitting. The first R piece, and then the remainder, the padding in a sense. Here too there's there are columns, R many columns that are important that I used. The remainder is basically like padding. They're just going to vanish under A. Now reading this off, these tells me that A times V equals U times sigma. Okay, and sending V to the other side, I have this, but V is orthogonal, which means that V inverse is the same thing as A V transpose. And that's how you, that's the singular value decomposition. Now in this diagram, there is the sigma that we're seeing. Well, think of it like this. If I were to take this and factor out the sigma, I get, so sending this to the other side and sending that to the other side, I have that sigma is equal to this guy. Okay? So sigma equals V A U transpose. So somehow it's the transformation that goes from here to there. Okay? Keeps the horizontal, sends it to the horizontal. That's that sigma tilde part, the left, top left corner. The remainder are zeros. That's not important. So what you want to do is think of this board as the world of Pac-Man, so that when something goes off from this side, it comes into the same board from this side. Okay, it's like waka waka waka. And then if you go up from this board, you come up from here. Okay, waka waka waka. So this sigma matrix is really here. Okay. But then I can go up as well, and that's going to be sigma transpose. Okay? And if I wanted, I could go up from here to there as well. That's also sigma transpose. And while we're at it, we might as well go from here to there. That gives you A. Okay? And further, I can see this. So these are all like universal diagrams, if you want. So I have also a better formulation for this. You see, all I need to do is to follow the arrows. I go down, so that gives me sigma, and then I go up, that gives me sigma transpose. So this really is this. Okay, it's a diagonal matrix. And likewise, this guy is going to be the other way around. Right? So first sigma transpose, then sigma. In other words, the diagonal matrix that is generated for A transpose A using the spectral theorem, I'm telling you, is this matrix. Okay, let's verify this. I'm going to delete that. I'm just going to write it. So we have this factorization. If you have this factorization, I can look at this product. Okay. So what is this? That's the first guy, and then transpose times this. Okay, expanding this, you have V sigma transpose, U transpose, U sigma V transpose. U is orthogonal, so U transpose U is nothing, it's identity. Okay? So that's the spectral decomposition for this matrix, is what I said. Okay? So this matrix is exactly this matrix. And if you look at this box, it tells you the spectral theorem. That's exactly the content of it. Okay? So this is this. I didn't get to dynamics, but okay, I'll leave this here. Any questions about this? I want to do some examples.
So why'd you remove the U transpose U again?
Because U is orthogonal. Yes. And if I were to do the same thing with the order is switched, let me leave that to you. So if I were to look at that box over there, this would turn into U sigma sigma transpose U transpose. So that would be also the spectral decomposition applied to this other symmetric matrix. Yes, it's the identity matrix. Yes. Okay, so here's an example. Now, if you were to go through these calculations, like that also gives you an algorithm, of course, to compute the singular value decomposition. And of course, if you're using a computer algebra system, you just say SVD of this, and it just produces for you this decomposition, or some variant of it. So let's consider this. So what do I need to do? I need to first look at this A transpose A matrix. A is 2 by 3. So this matrix is going to be a 3 by 3 matrix. Let me fast forward this calculation. Turns out to be this. 70, 140, 40, 140, 200. As expected, it is symmetric, as you see. Okay, it's 3 by 3 and it is symmetric. Spectral theorem tells you that the eigenvalues are positive or non-negative. You do some calculations and you realize that the first eigenvalue is 360. The second eigenvalue is 90. The third eigenvalue is 0. Okay. Okay. So we have these. Now taking the square roots of this, I get the singular values of A, right? Sigma 1 is going to be the square root of lambda 1. So if I were to take the square root of this, what do I get? 6 root 10. And then sigma 2 is going to be the square root of this. That's going to be 3 root 10. Okay? Now my sigma matrix is going to be a matrix of the same form as A. And it's going to be a block matrix. I need 2 spots for the diagonal part, and then I need to pad the remainder using zeros. That means that my sigma matrix is going to be like this. 6 root 10, 0, 0, 3 root 10. And this is the padding. So that now I have a matrix of the same form as A. Okay? Now in this case, it turned out that there's no 0 block here and there's no 0 block here. It can happen. Because essentially the reason why this happened is because the rank of A is 2. So here you don't need any padding. But this is your sigma matrix. This is the analog of that diagonal matrix that the spectral theorem generates. And then computing eigenvectors for this, this, and this gives you V. Okay, let's do that. There. These calculations are in the book, so I'm just fast forwarding all this. That's the first eigenbasis vector for A transpose A. Second one is minus 2 over 3, minus 1 over 3, 2 over 3. And then finally I have 2 over 3, minus 2 over 3, 1 over 3. Yes, and finally, you look at, so this guy is going to be scaled by lambda 1 if I were to apply A transpose A to it. And likewise, the second column, when I apply A to it, is going to be scaled by lambda 2. The third column is going to go to 0 when I apply A, because that corresponds to lambda 3, or A transpose A, sorry. If instead of applying A transpose A to these, if I were to apply only A, I get the U vectors. Okay, so because A times V has to be U times sigma. We know A, we know V, we know sigma. Over there, U is the remainder. Now in this case, it turns out that, where is this? Yeah. Now you see, U is going to be the first matrix when you're writing this down. We have this, we need this. This is a 2 by 3 matrix, this is a 3 by 3 matrix, which means that this has to be a 2 by 2 matrix. So you write U down, and it turns out to be this. Divided by root 10, 1 divided by root 10, 1 over root 10, minus 3 over root 10. Okay? And finally, you have all these matrices. And of course, if you had started with a symmetric matrix A, then A transpose would be the same as A, and so on. So we would just be doing the spectral decomposition for A squared, literally. In general, of course, A transpose is slightly different than A, but you get to multiply. There's so much more I wanted to say. But any questions about this example? It's rather straightforward, the calculations. It's just that it takes a while. It has a bunch of interconnected steps. Okay. So let me give one more example. And this is indicative as to why the SVD is so important in data science and machine learning. So here is sort of another example. typically your matrix in applications is either its number of rows is too large compared to the number of columns, or the other way around. Let's say that it's like this. So you want to use this in the context of, for instance, recommendation systems, say on YouTube or Netflix or whatever. Now, each column is going to correspond to a user. Netflix has millions of users, okay? It also has a lot of films, but compared to the number of users, it's minuscule. And each row is going to correspond to one film or show in the catalog. And what do you put here? Whatever this user thought of this film, okay, the review. Is it a thumbs up, a thumbs down, whatever. Now what you do is, if you were to look at A transpose, now this is going to be something like this. Okay. So when you multiply this, even though the number of columns were originally very large, now you see it's a very small matrix. It's not a very small matrix, but it's relatively small. And it's a square matrix. It turns out that this matrix encodes the correlations between these entries. So you want to say something like this. If most entries for two users match, the remainder should match as well. So like people, like things. Okay, that's the idea. And so this encodes the correlations or covariance, whatever you want to call it. And the singular values, which you ordered in descending order, really tells you sort of the important correlations. So this piece is the most important part, and so on. Unfortunately, I'm out of time. This is a beautiful subject. If you want to talk more about it, I would be happy to, but this is all that we have time for this. Tomorrow we're going to do dynamical systems. Thank you. Okay, let's start. Good morning. I just wanted to mention some more terminology regarding the singular value decomposition, and then we're going to discuss some dynamics. So if you have a matrix A, arbitrary, of rank R, then the singular value decomposition writes A as U sigma V transpose, where U is an orthogonal matrix, V is an orthogonal matrix, sigma is this block matrix, block diagonal if you want, and only at the top left corner there are non-zero entries, and this sigma tilde is an R by R diagonal invertible matrix with diagonal entries, non-negative numbers, or rather positive numbers. And just like we did in the context of the spectral theorem, of course you can write this first decomposition as a sum. That's also something that is important. The terminology is that these sigma i's are singular values of A. Columns of U, the left matrix, are called the left singular vectors of A, and the columns of V are called the right singular vectors. In the context of principal component analysis, left singular vectors are also called principal components in feature space, or eigenfeatures. And likewise, the columns or the right singular vectors of A are also called the principal components of A in the experiment space, or in other words, eigenexperiments. These are also terminology. This is also terminology that people use. And that's that. So now, dynamical systems. More specifically, we're going to be looking at linear dynamics. And the idea is that, so dynamical systems is a tool that you can use to model something whenever there's some time of evolution. So this is about modeling something that has a time evolution. Originally, or one of the most important cases of this are, of course, differential equations. But also difference equations and other things. We're going to see examples of these. Let me also mention, for instance, that if I were to look at this shift transformation rho acting on signal space, that is an example of a dynamical system. And of course, we're going to call a dynamical system linear if this time evolution is somehow modeled using linear algebra. Okay. Now, there are different versions and flavors of dynamics, as with any other thing in math. So you can sort of do dynamics more in the context of like applied math or mathematical ecology. In terms of, so this you can use in the context of perhaps policy making. But also you can think of it from an abstract point of view. I'm coming at dynamics from a more abstract point of view in my own research, but let's first look at some more reasonable examples that are more related to applications. So one very popular example in mathematical ecology is something called the prey and predator systems. So I want to think of it like this, okay? So I have two species that I'm considering. One of them is, let's say, owls. I believe spotted owls, or owls, and the other ones are rats. So let's say that prey, some rat population, predator is some owl population. Okay? So, and we're going to try to sort of model their interaction in a very simple way. I'm not really claiming that this is realistic. But what we can say is this. So rats are being eaten by owls. And I don't know, in this specific model, I don't care how rats survive, essentially, how they eat and how they grow and so on. If I have lots of rats, okay, in the next generation, the number of rats should increase also. And the number of owls should increase also, okay? On the other hand, if I have lots of owls, let's just say, for the purposes of this model, that in the next generation, the owls, because they're going to be able to breed better, let's say they're going to have a lot more options. In the next generation, the owls are going to be more. But the number of rats are going to decrease because owls eat rats. That's sort of like the general idea. Okay? So now I want to sort of like think of this in terms of matrices. So let's say that, and so how am I going to distinguish these numbers? Let's say that with uniform intervals, let's say, I just like measure how many rats I have in a certain space and how many owls. So let's say that each month, on the first day of each month, I go out into the field and I sort of count everything. Somehow I'm able to do this. So let's say that O of n is going to be the number of owls on month n. So number of owls in month n. And likewise, R of n is going to be the number of rats in month n. So I want to think of the relationship between O of n plus 1, right? So the number of owls in the next month related to the number of owls this month. So I want to say something like this. Okay. And I'm assuming, for the purposes of our discussion, that whatever relationship that we discussed here are, these relationships are linear relationships. Okay? So this should depend linearly on R of n and on O of n. So this will be some number times R of n plus some other number times O of n. And likewise for this. Okay. Now, based on this heuristic here, the larger this is, the larger this should get. Okay, because the more rats I have, the more rats I'm going to obtain next month. So this should be a positive number. This should be a negative number, you see, because if the number of owls increase, then that means that more owls are going to hunt more rats, and that's going to have a negative effect on the number of rats next month. And here, this should be a plus because the number of rats this month means, so the more rats I have this month means that the owls are going to have more food to eat. So that's going to have a positive effect on the number of owls next month, and likewise here. Okay. So what we're going to do is let's just fix 3 of these numbers. So these are positive numbers. So I'm going to write it like this. Instead of having a minus here, I'm going to put a minus here. And this is now a positive number. And I'm going to leave this as a parameter, and everything else is going to be fixed. How do you fix this? You sort of like do some sort of statistics, essentially. Maybe over time you average your measurements, and that gives you sort of like a matrix. This is not really that important for the purposes of, for our purposes, but so the example that they give in the book is like this. This is 1.1. This I'm going to leave as a positive parameter p, or non-negative parameter p. This I want to be 0.4, and this I want to be 0.5. So these are empirical numbers, okay? I decided what my model should be, and I did some experiments. I collected all that data, and I put them into these places. Now this p is called the predation parameter, right? Because the larger p is, the more owls are better at hunting rats. So p is the predation. I want to leave this as is, okay? And so, of course, this is a linear system of equations, and I know at this stage that I can sort of write this in a matrix form. So if I were to do that, I get this. I'm going to have one column that tells me the state of my system at time n+1, month n+1. And then I'm going to relate it to the state matrix, the state vector, at time n. And of course, this is 2 by 1. This is 2 by 1, which means that here I should have a 2 by 2 matrix. And of course, that's going to be these coefficients, right? So 1.1 minus p, 0.4, 0.5. So that's, let's call it A. So this A is my transition matrix or transfer matrix or propagation matrix. Depending on what you're doing, this has different names. So you see, really, making time go one step further, so going from n to n plus 1, is all about applying this matrix. And so if you wanted to talk about the asymptotic properties, so over a long period of time, that would require you to apply A many times, right? So if you want to see what is happening at month 100, that means that you're going to start at R of 0, O of 0, and apply A 100 times to it to get R of 100 and O of 100. So state, let me write this. On month 100, let's do it like this, 120 in 10 years, right? So you're trying to figure out, based on this simple model, what is going to be the outcome. Well, this is just going to be R of 120, O of 120, number of rats in month 120 and number of owls in month 120 equals. So you see, from going here to there, having A here allows me to decrease the number by 1, which means that if I want to get to 0, I need to apply A 120 times. And this, of course, is your initial condition. Initially, when you started this experiment, these are the numbers that your experiments told you. And over time, it changes. Okay? And you see, this is why powers of a matrix turn out to be sort of like a time evolution. So let me write this. This is the initial state, initial condition or initial state. Some people also call it the seed. Okay, so far? And so I want to be able to take large powers of a matrix. And this is where diagonalization, if possible, comes into play. So let's think further. Maybe let's also mention what this P would mean here. If P were 0, that means that my owls are terrible at hunting rats, and they're actually unable to hunt rats. And you see, this is not a very accurate model, but because I'm saying that owls eat rats, but somehow if owls don't eat any rats whatsoever, they still grow a little bit. Or rather, they can still survive for a while. Perhaps it is accurate in that sense. Now that I think about it. Anyway. So diagonalization is an important thing then. And the first thing for diagonalization is, of course, looking at eigenvalues and eigenvectors. And I want to keep that parameter as arbitrary, okay? I don't want to hard code a specific number there. That's why I'm keeping this parameter as is. Of course, originally we started with 4 numbers being unknown, 4 numbers essentially being parameters, but then there's this trade-off. Either you want your model to be accurate, but hard to handle, or it's going to be simple, but maybe not that accurate, okay? So this is like a trade-off. You say, okay, so these are all parameters really, But I'm more confident with these numbers, so I'm just going to keep them fixed. And this one, I'm not that confident. And maybe there's some fluctuation there and so on. I want to figure that out. So, so my matrix was this. Let's look at the eigenvalues. So I look at the characteristic equation. P minus 0.4, lambda minus 0.5. Okay, so I want to solve lambda in terms of P, this predation parameter. Okay, so writing this out. I did this somewhere here. So this, you open this up and so on. Yeah, this gives this 0.55 plus p times 0.4. Okay. So this is a second order polynomial in lambda, so I can apply the quadratic formula to solve for lambda. And when I do that, I get this. So organizing this a little bit, simplifying the expression and so on, I get a much better looking expression, and it is this. So you see, there's this critical value for the predation parameter. This is 9/40, which is less than 1/40, 10/40, which means that this is less than 0.25. Okay? So what happens here? This is my parameter space. Okay? Here is 0. Here's this critical value, 9/40. There's a phase transition. Okay? The system changes in a sense. If your P is less than 9/40, then this expression inside the square root is a positive real number, which means that you're going to have two distinct real roots. Okay? So here, distinct real eigenvalues. Let me just leave it as this. If P is exactly this critical value, then this is going to vanish, and I'm going to have both lambda 1 and lambda 2 4/5. So this is when you have repeated real. Roots. And if P is further than that, so if there's a lot of predation, then that means that you're going to have complex conjugate roots. Okay. Let's also note this. When P is 0, for instance, I'm going to have here, so now let's draw the spectrum. Then somewhere here, I know that when P is exactly 9 over 40, I'm going to have repeated real roots, and they're going to be 4 over 5. Okay? So I'm going to have one point here inside the unit disk. That's going to be my spectrum. Before that, I have repeated real, which means that as I'm going here, as I'm decreasing my predation parameter, this eigenvalue that is repeating splits into two pieces and starts to grow apart. Okay. In particular, when P is 0, okay, then write it. So let's compute it. When P is 0, what happens? Let me do it here. Four plus or minus root 10 times root 9 over 40. Okay, so that's root 9 over 4, so that's 3 over 2 divided by 5. So one of the roots is going to be 4, so let's do it like this, 8 plus or minus 3 divided by 5, by 10. Okay, so the smaller eigenvalue is going to be 1 over 2, so 5 over 10. The larger eigenvalue is going to be 11 over 10. Okay, so this was 4.5, so 4 over 5. It's going to be to the left, the first one. The other one to the right. And as I'm increasing my predation parameter, they join exactly at 4 over 5. Okay, so this guy is going this way, and this guy is going that way. And if I increase even further, what happens is this. If P is larger than 9 over 40, this number inside the square root is going to be a negative number, which means that this is going to produce for you an I, right? Which means that this is going to be a complex conjugate. These are going to be complex conjugate. But the real part is going to be the same, which means that as you're increasing your predation parameter, what's going to happen is that this time your eigenvalues are going to split along this. They're going to start going up. One of them is going to go up, the other one is going to go down. And of course, eventually, they're going to leave the, so somewhere here is going to be far away. They're going to leave the unit circle. Okay, so if you want, you can draw the picture too, of course. It's going to be like this. Any questions about this so far? So now what does this tell us? If I have no predation, then I have distinct real roots, which tells me that my matrix is diagonalizable. Okay? You know this because no matter, so for any square matrix, if its eigenvalues are distinct, it has to be diagonalizable. And so you're going to have two eigenvalues. Lambda 1 is the larger one, let's say, and then lambda 2 is the smaller one. So up to some coordinate change, A is going to be lambda 1, 0, 0, lambda 2. Okay? Now, lambda 1 is larger than 1. Lambda 2 is less than 1. So now, if you were to change your coordinates, whatever this matrix is, this matrix of eigen vectors, now instead of using this R and O coordinates, if you were to switch to whatever coordinates this gives, that tells you that instead of taking the 120th power of A, you can just take the 120th power of this diagonal matrix. Because you see, so for instance, let's look at A of 2. A multiplied by itself, using that guy. And let me call this middle matrix D. Of course, this is PD, P inverse, P, D, P inverse. And of course, these two cancel out. This is what happens. And of course, the same idea holds no matter what the power is. Okay? So what you can say then is that the state here at month 120 really is P lambda 1 to the 120, 0, 0, lambda 2 to the 120, P inverse R of 0, O of 0. But you see now, in the case when P is less than this critical value, I know that this guy is less than 1. And in fact, even when P is the critical value. In any event, if you have a number that is less than 1, and if you take powers of it, this decays to 0. So for large months, number of months, this is pretty much 0. So all you need to do now is to just read this first one. Okay? So you see, when you're, so if, because the main idea is to take iterates of a matrix, once you have a diagonalization, then all vectors associated to eigenvalues of modulus less than 1, they're going to decay. They're going to decay to 0. And all eigenvalues, or all eigenvectors, or all vectors associated to eigenvalues more than 1, they're going to grow to infinity. So that growth tells you population explosion, essentially, in this context. Okay.
For the rats. For the rats.
Not necessarily. So, because you see, at this stage, I don't know what this eigenvector is. I would need to compute the eigenvector to figure that out. Yeah. It really tells you, this is sort of perhaps why it is not super realistic, that if you have no predation, as in that case, eventually everything will be proportional to the eigen space associated to lambda 1. Okay, so let me draw a picture. I don't want to do calculations, but let me draw a picture. This is again for, let's say, p less than 9 over 40. Very little predation there is. I know that the matrix is diagonalizable because it has distinct real roots, and the eigenspaces are linearly independent. So let's say that one of the eigenspaces is this, the other one is this. I'm not saying that they're orthogonal because my matrix is not symmetric. I don't have that. So this guy is going to be the eigenspace associated to lambda 1. This guy is going to be the eigenspace associated to lambda 2. Maybe I should write it like this. Eigenspace of lambda 1 and eigenspace of lambda 2. Now, lambda 1 is larger than 1, which means that this is expanding. And lambda 2 is less than 1, which means that this is decreasing. It's contracting. And so really I should say 0. So I'm really looking at this situation. Because you see, why didn't I just say p has to be less than 9 over 40? Because I really want, in this situation, one of these eigenvalues to be outside the unit circle. But as I'm increasing the predation parameter, this lambda 1 is going to come closer and closer to 4 over 5, which means that for some value that I could compute if I wanted, it's going to be exactly on the unit circle. Okay? So I didn't want that. I want lambda 1 to be larger than 1 so that it is expanding. Now this, let's say that I have an eigenvector lambda 1, v1 for lambda 1, and an eigenvector v2 for lambda 2. v1 and v2 is a basis, which means that any vector whatsoever can be written as a linear combination of v1 and v2. Any vector, of course, tells me one initial condition. And if I were to apply a n times to v, this is the same thing as c1 lambda 1 to the n v1 plus c2 lambda 2 to the n v2. Okay, this is larger than 1, so this piece is going to go to infinity, but it's going to go to infinity along a certain slope. Whereas this is always going to go to 0 because this number decays to 0. Which means that if you were to start with a point here, let's say, this was your initial condition, you look at the components. This is the lambda 1 component and this is the lambda 2 component. As you apply a, as you make time pass, what's going to happen is that this piece is going to decay to 0. Whereas this piece is going to go to infinity, which means that this is what's going to happen to v. So eventually it's going to be asymptotic to this eigenspace. That's what it's telling you. Now, whether or not rats or owls are going to survive depends on the slope. Any questions about this? If, of course, so let me just say it like this. There's a unique number p such that, somewhere here, such that at this position, so when your predation parameter is exactly this, lambda 1 is going to be exactly 1. Okay, so let me say, call this p star. That's going to be your exercise to compute. Of course, the underlying idea is that the eigenvalues of a matrix depend continuously on the parameters. So as I'm moving the parameter a little bit, the eigenvalues are going to move a little bit also. So you see, this lesser eigenvalue is always going to be less than 1. It's always going to be less than 4/5. But lambda 1 starts at a place that is outside the unit circle, and as you're increasing the predation parameter, there's this specific value, p star, where lambda 1 is exactly 1. Okay? Now, I will still have distinct real roots because they're still not joined at 4/5. But one of the eigenvalues is 1, which means that any eigenvector associated to lambda 1 is going to be a fixed vector. Okay? So let me give this definition. V is fixed under A if AV equals V. Okay, so I apply this A matrix to my V, my state stays the same. Another word for this is an equilibrium state. There is this P star such that if P is equal to P star, my larger eigenvalue is 1. Okay? Any eigenvector associated to it is going to be an equilibrium state. Now, based on exactly this idea over here, again, I have distinct real eigenvalues, which means that I have an eigenbasis. Which means that if I apply a to the n, so n times I'm iterating, to an arbitrary vector, what's going to happen is this. C1 times V1, eigenvector associated to lambda 1, which is 1 in this case, plus C2 times lambda 2 to the n V2. Okay? This is the case when P is equal to P star. Lambda 2 is still less than 1, which means that as I increase n, this is going to again vanish to 0, which means that asymptotically, this is what you're going to get. Okay, so that's an equilibrium for you. System reaches equilibrium. Here there's an explosion, population explosion. Now next week, when we start talking about PageRank, this is also the situation. It's going to turn out that in the context of PageRank, you have a bunch of eigenvalues. The largest one is 1. The other ones are less than 1. And this PageRank vector, this $25 billion vector, is a certain eigenvector associated to the eigenvalue 1. It's this equilibrium state of the system. We're going to be getting more into detail about this. But of course, let me also finish this idea. After this, so if my predation parameter keeps increasing, what's going to happen is that, well, both of the eigenvalues are going to be less than 1. In which case, everything is going to, what do you call it? They're going to go extinct. But of course, there's this other parameter, which is why this model is not very realistic, which says that if predation is super large, then somehow the system is still going to survive. Like people are, species are still going to survive. Okay. And again, this model predicts infinite growth, which is why it's not realistic. And if you want to start using or start considering finite growth, let's say that eventually there should be scarcity or something like that, or somehow competition should increase eventually, then you got to start working with nonlinear models or stochastic models. If you take a class in differential equations, typically they mention this logistics equation, which sort of like has sort of like that type of behavior. Yes.
Stochastics means
random.
Consistently random, like not just arbitrarily, like totally random, but it's like.
It could be that way. It could be inconsistently random. That is about whether or not the system is identically distributed. Yeah, the distribution could change over time. Yeah.
So stochastics is
just random. Just means random. Some randomness. There's some randomness. Yeah. So, for instance, you can immediately turn this into a random model by saying that P is a random parameter between, it's a uniformly random parameter between 1/5 and 1.
Would you say, out of curiosity, if you were curious about that, is that more in the direction of like stats, or is that more in the direction of like differential equations, or somewhere in between?
Probably it's somewhere in between. Yeah. Probably in this case, because this is a very simple model, I would call it statistics, but there's also something called stochastic differential equations. That turns out to be important in the context of, for instance, white noise or Brownian motion and everything. These are like the prime examples of random processes. But yeah, I wanted to mention one more item, another model, and this is called the Leslie model. On Monday, I'm going to talk a little bit more about dynamics, but from a more sort of higher vantage point. I'm going to mention a certain method that is rather old, but it's been getting quite a bit of attention the past 15, 20 years from the engineering community. So I think it would be good. And it is this so-called Koopman operator method. I want to mention something about it, and I want to prove an ergodic theorem, or at least mention an ergodic theorem, which is also this underlying idea of this random surfer model that the PageRank algorithm is based on. But before that, let's look at this. And so this is about the Fibonacci numbers, okay? Fibonacci numbers they go like this. So 0, 1, and then for the next stage, you add the previous 2. So that's 1, and then that's 2, and then that's 3, and then 5, and so on. And there's a bunch of different things about this, but let's think of this from a modeling point of view. Fibonacci's model was this. He was counting pairs of rabbits, and you start with one pair of baby rabbits, and I'm going to call it a juvenile pair, okay? In the next stage, this grows, and now we have an adult pair of bunnies, of rabbits. In the next stage, this pair survives, so they're still adults, but they also generate a new pair of juvenile rabbits. Okay, so this is the idea. At each stage, an adult is going to survive to the next stage, next time, but it's going to also generate a new pair of juvenile rabbits. And for a juvenile rabbit to generate more rabbits, you need at least one time progress. Okay? So this is what happens. And then now J becomes an adult in the next stage. Okay? It grows like this. Now, adult survives, generates a juvenile pair. This juvenile pair becomes an adult pair. Now I have this adult pair here, and I have this juvenile pair coming from this adult pair. Okay, it goes on like this. And of course, the numbers, as you can imagine, turn out to be this. This is 1, 1, 2, 3, 5, and so on. This is how we generate the Fibonacci numbers, or one of the ways of generating this. Just like I did before, I can look at the number of juvenile rabbits at stage n plus 1 and the number of adult rabbits at stage n plus 1. And relate them to the numbers in the previous stage. Now, what should this stage matrix or transition matrix should be? Well, this has to do with, so juvenile rabbits do not generate any new pairs, which means that this has to be 0. And any adult pair generates a juvenile pair. So that should be a 1. How about this? Any juvenile pair in the next stage is going to be adult. So this should be 1. And this should be 1 as well. Okay? So this is your transition matrix now. Okay? And of course, what is the nth Fibonacci number? I can say that f of n, nth Fibonacci number, is the sum. It turns out that this is a diagonalizable matrix, and its characteristic equation is exactly the equation that is satisfied by the golden ratio, which is 1 plus root 5 divided by 2. So this is lambda squared minus lambda minus 1, I think. And phi, this famous number, which is the golden ratio, is the larger eigenvalue of this. The other one is smaller than 1. In fact, it's negative. And of course, people would say that, oh, the ratios of the Fibonacci numbers, so 1 over 1, 2 over 1, 3 over 2, 5 over 3, and so on, converge to this guy. Why? Because it's the larger eigenvalue. Whenever there's an important number in math that seems like it is like bizarre, ad hoc, it's probably the eigenvalue of a certain operator underneath. Now, in the next problem set, probably you're going to see some problems about this. So in the Fibonacci model, your rabbits are immortal. They keep generating juvenile pairs month after month. But you can also think of what happens if after a certain period of time they die. So probably you're going to have a problem related to that in the problem set. But that's it. On Monday we're going to talk a little bit about ergodic theorem and Koopman methods. And tomorrow we're going to have review. And on Friday we're going to have the exam. Thank you. I'll see you later.